So for week 6, we're going to be looking in detail at what's called rigid body equilibrium. I've kind of mentioned that in passing a couple of times, rigid body equilibrium, but we'll just quickly go through the differences between that and particle equilibrium. So again, you're talking about something that's got static equilibrium. For particle equilibrium, we've gone over this a few times now, but it's just worth reiterating the difference between these two. So for particle equilibrium, what you're looking at, you can use that if you've got, where would I start with this one? I'd probably actually start by drawing on the primary forces, which in this case would be the weight. And then we'd know we had forces acting along the line of action of these ropes. So we've talked about those simplifying assumptions that we can make. So we know that any reaction forces are going to be in line with those ropes because they're flexible. And we also, so therefore we can see that the lines of action of all three of the forces intersect at a single point, and that's how we know we can use particle equilibrium for this. And so when we're doing particle equilibrium, when we're drawing a free body diagram, then we're just looking at identifying the point where all those forces intersect. So let me do it in black. Just change the thickness of that. And once we're looking at that, we can think, what are these ropes doing to that point? Well, we must have a force going this way. It's keeping that point from falling down. So there must be a force this way, and there must be another force in the other direction. We don't know exactly how big it is, but there's those forces. And so in terms of what a free body diagram is, for this type of problem, we just grab that little particle, draw it on its own, and draw the forces. Now, I'm not going to calculate what they are here, but I'm just going to quickly draw them on. I kind of know that the y's, so the y component of these must add up to the total, or must be opposite the total magnitude of this one, and the x components of these two must balance each other out. So you can kind of get a bit of an idea of what you should be drawing. And so let me just think something like that. Maybe this one's going to be a wee bit shorter because it's got to have the same x component as the other one. So to balance those x components, it must be a little shorter, otherwise the x, because it's got a lower angle, otherwise the x components wouldn't balance. Maybe something like that. You've got a force due to the weight downwards like so. So for that situation, we've got a couple of rules that we can use for particle equilibrium. And so the rules we can use, I think I had something here, just a minute. Maybe not. And so the couple of rules we could use is we could solve this graphically. And so let's just grab this, put it down here. To be in equilibrium, those would all have to make a closed path. And so we could put them all nose to tail. Like so. Just make sure I've got a small eraser here. Yep. So we know it's going that way. We don't exactly know how far it's got to go. We know this one is going this way. We didn't know exactly, it wasn't too far away with my guess. Look at that. And so if they were in equilibrium, we know that they would join up and they would go back to zero. So this one should be a little bit longer. But otherwise, we were pretty close. And because it's not at the right point of application, we'll just make it dotted. Okay, and so a closed path means static equilibrium, or we can use the fact that it must be a closed path in order to figure out some missing forces, just like I did there. So you just adjust the length so that they go back to zero, so you know where they cross. Or we had a couple of rules we could use, so let me just write those out if I can. So the rules are the sum of the F components must be equal to zero. It's annoying. Equals zero. And we also know that the sum of the y components must also be equal to zero. And so we had those rules. I might just do those one above the other. And so if it's static equilibrium, that must be true. So you can use that to prove it's true, or you can break these down into their components, equate components, or come up with two simultaneous equations, and then you can find two unknowns. So either you could find a force and an angle, or you could find two forces. You could also, we haven't done it, but you could also find two angles, and you could find a force and an angle. So it could be force on one of these ropes and find the angle on the other one is what I'm meaning. So it doesn't have to be the force with its own angle. So you can always find two unknowns. Why? Because you've got two equations. Just making this a bit bigger. So we've got those rules now. So now we're moving on to rigid body equilibrium, and it's very similar to particle equilibrium. The steps are similar, but it just adds a couple of conditions. So if we were looking at the forces here, the first thing you do again for this type of problem is you draw a free body diagram of whichever element you're interested in. So I might be interested in this beam here, and then you just kind of simplify things so you can see what's going on. So I might draw my primary forces. You might also have to add weight, but often they'll just tell you to ignore the weight because it's very small compared to the main forces. And so you might have applied forces like so. One's 10, one's 15. You might also have the weight, which in this case, okay, they've cut off a bit of the flange here. So this is an I-beam. So if you looked at it from this direction, if you were looking at it that way, you would see an I shape. So it would look like that. So it's an I-beam. They've cut off a bit of the flange, but it wouldn't affect things much. This is a uniform mass per unit length. So the centroid will be in the center of this beam. So we might have a weight heading down like this as well. I'm just thinking the reason I'm including that is because this is only 10 tons, this is only 1.5 tons. And this here is a 6 meter long I-beam, so it's going to be pretty heavy in itself. So I don't know if you would want to ignore weight in this case. So we'll just add on our weight as well. And so what we're doing is we're just taking that object and we're just drawing it without any other connections and just with forces. Now the next thing we'll learn about in this week is that when you're drawing this free diagram, we don't want to draw those supports. We want to show what forces they might apply to this beam. And we'll get into the details of that just shortly. But this here is a pinned connection. So there's like a pin going through there, a bolt going through there. So it would be free to rotate. And so it can't have any moment associated with it. It can't resist a moment. If I was to, ignoring the weight of this, if I was to lift it off, it would just rotate. But what it can do is it can make a force this way. So there might be a force like so. Well, let me just try and keep this neat. It takes a little bit longer, but it's probably easier to understand. Oh, what I should draw here is there would be a little hole through there because it's a pin connection. So there would be a little hole through here. But I could draw, this pin could resist someone pushing it this way. And so if someone was to push this beam this way, this pin connection could resist it. So we might have a force like that. And it could also resist the beam from pushing down. It'll stop the beam falling down at that point or translating down at that point. So there would be a force in this direction as well. So we might have an, what would we call that? Maybe we just, because this is the point A, we just call that RAY, RAX, something like that. On the other end, we've got a roller, and you might remember when we're doing that the reaction for a roller on a smooth surface is always perpendicular to the roller. And so the only force we get on this end from the reaction would be an upwards force like that. And so we're going to look at this in more detail for different support conditions and that sort of thing. But the basics is you're doing something very similar. You're just taking this beam out. You're not drawing any of the other gubbins, so you're not drawing the supports or anything like that. You're just drawing the object you're interested in. I'm not even drawing these secondary members, they're called. Just drawing the forces. You probably want to label them, 10 kilonewton meters, 15 kilonewtons. We don't really know what this is, but it might be a few hundred grams. So it might be something like, it's 1.5 tons, I don't know, might be 2 kilonewtons or something like that, the weight of that beam. Now, whether I should do it like that, it's a good question actually. When we get to this later, so what I'm doing here is I'm taking all of that beam and I'm squashing it down into a single point. But what we'll find when we're doing these types of problems is we might actually have to draw that as a line load, because it might be the case, and I'll show you why in a minute. Well, you'll find out why when we're doing the examples, when we get through this stuff. But we might have to draw that rather than drawing a force like that. Just do it like this. we might have to draw this as a line load if we want to find the internal forces in this beam. And so that's the next thing that we're going to be looking at, is we're going to look at internal forces as well. I'll get to that just after I've talked a bit more about the rules that you can use for rigid body equilibrium compared to free body, particle equilibrium. So what we're going to learn to do is to draw a free body diagram like this. That's everything we'd need. I'd probably have to just say this might be weight, small w, because it's weight per unit length. That one, weight per unit length, it's a UDL. The rules we have, when you get to these ones, your graphical solutions are not so useful. You might still use them to combine some forces if you wanted to, but mostly we'll just be working with components when we start working with these types of problems. And so we might have Fx, Fy, but for rigid body, we have to add one more. And so what we have to add is, let me just get my equation writer working. We have to make sure that all the moments also add up to 0. So we need 3 rules this time. Now, for here, we had 2 equations, so 2 rules, and we could find 2 unknowns. This time we've got 3 rules, so we'll be able to find 3 unknowns, and that's why, for example, in this one, you'll notice that there's 3 reactions. So we might call this RBY. I haven't labeled that one. And that'll usually be the case. You usually find out you've got 3 unknowns because you've got 3 equations. And so you might be asked to show there's equilibrium. They might give you the support reactions. It doesn't happen so much. Or you might be told to find these support reactions. You're going to use these equations to find those support reactions. Now, there's one more thing we need to think about, and that is because we don't have all these forces going to one point now, it becomes more important to understand how does this force, so if this beam's not going to go downwards, somehow this force has to be carried to this support. And maybe this force is going to this support, might get a little bit of that force going to the other support. It's hard to say, you have to do the calculations to figure out. But somehow these forces are getting to these supports. And the reason they can get there is because there's internal forces in this beam. So this beam is deforming, that's causing forces inside. And we've come across it a few times now, but if you want to try and find the forces inside something, or to want to try and see the forces, what you can imagine is just cutting it. So this is the same beam, we've cut it, and what we're going to do is we're going to use equilibrium to try and find out what these internal forces are. So we've got a shear force here. There's no axial force, you might remember those terms, because there's only vertical forces here, but there might be a shear force and there might be some kind of moment that you would need to apply. So we'll talk a little bit about that. So that's just a quick overview and introduction. Don't think there was anything else I wanted to say. Let me just zoom out so you can see it all. And so this is just another rule or another thing we're going to have to do this time, is to try and find internal forces. I guess there was one more thing I wanted to mention. For this particle equilibrium, if you look at this one here, it's not the case that all those forces not all the forces in that system would intersect at the same point. So these 3 are intersecting here, these 3 are intersecting here. But I could still use particle equilibrium in that instance, as long as I know maybe, I've got most of these and there's only 2 things I don't know at that point. Then I could take that point out first and do some kind of free body diagram of that and figure out what I needed to do. And then I could take the other point out, C, and I could do some kind of free body diagram and figure out what those forces were, and then I could solve the whole problem. So even though it's not the case that all the forces intersect at the same point, we can do it stepwise. We can take each point, we could even take point A, free body diagram, D, point free body diagram. We can take each point in turn, use particle equilibrium to solve it. So that was just one other thing I wanted to mention. Whereas this one, we can't do that. There's no point that we can take to solve that problem piece by piece. Okay, that's that. We'll now go on and we'll have a look at a bit more detail about these support reactions.